Okay, so we're going to do an optimization problem where we're going to consider the graph of y equals 4 minus x squared. So basically y equals 4 minus x squared is a concave down parabola that has been shifted up 4 units. I get that from 4 minus x squared. This is my attempt to sketch it to the best of my ability, and it's going to have to do. So a couple of things. First off, I want to make note that this particular graph is going to intersect the x-axis at positive 2 and at negative 2. And I can easily figure that out if I set 4 minus x squared equal to 0, see where it's equal to 0, and then solve this. So I can add the 4 over and then plus or minus square root. That'd be one way to solve it, but it should be clear that if x is 2 or negative 2, 4 minus that squared would equal 0. So what do I want to do? Where's the optimization piece come in? Well, what we're going to do is we're going to inscribe a rectangle in this parabola, under this arch here. And the way we're going to do it is we're going to make the top of the rectangle, the top two vertices, lie on the curve. So that would be the top of my rectangle, and then I would just sketch it down, come over, and this is a representative rectangle. Now I can draw any rectangle that I want. So for example, I drew that one because what I'm going to ask you to do is to find the rectangle that has the maximum amount of area. And it looks like it'd be somewhere around there. But I could, if you think about it, I can draw maybe this rectangle here where the two vertices are touching here and here. And it would be a thinner rectangle. It wouldn't have as much area. Likewise, I can draw the top of my rectangle up here where the two vertices are touching. And it also would be a thinner rectangle. And so it seems the reason that there must be a fatter rectangle or an area with the largest area possible somewhere between this horizontal looking rectangle and this vertical rectangle. And that's actually what we're going to be tasked to find. So, all right, when I do an optimization problem, I like to write down what it is I want to do. Well, I kind of told you what we want to do. We want to maximize area here. And to me, that's always important in an optimization problem. Understand what it is you want to do. We want to maximize area. So in order to maximize area, it would make sense that I would need an area function. So, all right, what are we talking about here? Well, area of a rectangle is going to equal base times the height. So now, in the context of this problem, how can I label what the base and what the height is? And so some people like to just say, oh, I'll just call the bottom here, call the base X, and call the top Y, and be done with it. But you can't necessarily do that because this isn't just a rectangle lying around in some empty space. It's on the Cartesian plane. It's on the XY plane. So that has to come into consideration. And so I would bring your attention to this point here. If we kind of for a second make it about, well, let's think about what this point needs to be in order to get this rectangle with largest area. Well, what would this point be? Well, I don't know what it is, so I know I can label it X comma Y. And from that fact, I can label some stuff on the rectangle now. So think about it. If this is the point X comma Y, how do I get there? Well, from the origin, I would have to go over X, so that distance there would be X, and then go up Y. And so now if you think about it, the base of the rectangle isn't X, it's actually going to be 2X because this distance is X, but also that distance would be the same, would be X. You say, well, why is it the same? Well, because this is an even function, y equals 4 minus x squared. What does that mean it's an even function? It means it's symmetric to the y-axis here. So whatever this distance here is going to equal that distance there. So I can say that my base is going to be 2X. Now, what's the height going to be? Well, it turns out the height is y. So I get this area function now, that area equals 2x times y. And when we do optimization problems, it's usually convenient to get the function in terms of one variable that you want to maximize. And so right now I have x and y. So you're thinking to yourself, oh, if only I knew what y was in terms of x on this curve, that would be fantastic. Well, obviously it turns out you do. You know that y is equal to 4 minus x squared. So I'm going to go over and chuck that in here. So I can write now a of x, because I have area strictly in terms of x now, is going to be 2x times 4 minus x squared. And if I was doing this, I would probably bust out a little distributive property here. Multiply 2x times 4 is 8x, and 2x minus x squared is going to be minus 2x cubed. And so, all right, where do I go from here? Well, it kind of depends on your approach. I like to come up with intervals. An interval for the function, in particular for the variable of interest here, which is x. So, all right, what is x? Well, x represents this distance here. I labeled it. Well, what can it be? Well, I know it can't be any larger than 2, right? Because then I would be outside the rectangle and I wouldn't be inscribing a rectangle. So I know the biggest I can make x is going to be 2, all right? Well, what's the smallest I can make it? Well, I'm going to say that it's 0. Someone might say that it's -2, and I guess technically that's not necessarily incorrect, but if I take all of the x values from 0 to 2, right, that's going to get me points all along this parabola, all along this side. Well, because this thing is symmetric, if I'm using all of those points as my top right vertex in the rectangle, I will get all the possible rectangles that can be drawn. So I can go from 0 to 2. The other distinction here is people say, well, shouldn't it be open? Like you can't really have x equaling 2 because think about it, if x is equal to 2, right, that would mean that this is the vertex of your rectangle. Well, your rectangle really wouldn't be a rectangle, it would be this flat line. And it turns out we can actually consider that, if we wanted to, something of a degenerate rectangle. So it's a rectangle of area 0. And some people have issues with that, and I get that, and I'm okay with that. And if you do, well, then no big deal. Just leave the interval open. But we can argue mathematically that it's not going to matter. Because if I close the interval, or if I leave it open, I'm going to come to the same conclusion. And maybe I'll talk about that a little bit more after we move on a little bit. All right, so what's going on here? I have my area function. I notice it's a polynomial. Well, polynomials are continuous. So I have a continuous function on a closed interval. What does that tell me? That tells me I'm guaranteed to have an absolute maximum and an absolute minimum on that interval. And that's basically the extreme value theorem. And I'm going to kind of do a little aside here. Make a little note. And I'm going to erase this in a second, but it's worth talking about. So what did I just say? Extreme value theorem, what is that? Well, basically, if you take any continuous function, so there's an example of a continuous function. If I look at that continuous function, so by the way, it's continuous because I can trace it without lifting up my pen. If I look at this function on any closed interval, so maybe I'm going to look at it from this point to that point. So I only want to look at the function on this interval. What's going to happen? Well, the extreme value theorem says that you're guaranteed to have an absolute max and a min. Extreme value theorem is just an existence theorem. And if you think about it, well, that would be the case here, right? It's pretty clear. In this case, I'd have an absolute maximum on the interval that I closed right here at this endpoint. And it looks like I'd have an absolute minimum right here. And that would occur at a critical point. And so that's basically the logic that I'm going to employ here, right? So I have my endpoints, so that's good. And I can get my critical points. And how do I get critical points? I'm going to go ahead and take the derivative and see where it's 0 or undefined. And so then how are you going to know? I'm not going to have a picture of this graph in my head. How am I going to know what's the biggest and what's the smallest? Well, we're going to test them. So in other words, we're going to plug them into the function, the original, and just compare the y values. So in this little example I drew here, this endpoint, when I would test it, would have the largest y value, and this critical point, when I would test it, would have the smallest y value. All right, so that's kind of what we're going to do here. All right, so here we go. Let's go get them. So it's time to get the derivative. So a prime of x. Oh, look at that. A prime of x is going to equal 8 minus 6x squared. Right? So the derivative of a difference is the difference of the derivatives. The derivative of 8x is 8, and the derivative of 2x cubed, if I use the power rule, is going to be 6x squared. So now what do I want to do with this? Well, I want to set it equal to 0. So I'm going to go ahead and do that. So I'm going to set 8 minus 6x squared equal to 0. All right? It's never not going to, it's always defined, so I don't have to worry about that, but I do have to see where it's equal to 0. So a couple ways we can solve this. Maybe I'll do this a traditional way. I'll add the 6x squared over. So I'm going to get 8 equals 6x squared. Then maybe divide both sides by 6, right? It's a pure quadratic equation that I'm dealing with here. What does that mean? It just means it's a square term but no x term, so I can do it this way. So I divide both sides by 6. I get 8 over 6 equals x squared. If I want to simplify this, 2 goes into that 4 times. It goes into that 3 times. And so now how do I solve for x? I'm going to go ahead and use the square root principle, which basically says take the square root of both sides. And the principle says plus or minus the square root of that non-variable side. There's some reasons why that you have to do that. We're not going to get into them now. And so I'm going to get plus or minus the square root of 4 over 3. And that's what x is going to equal. Now notice my interval is from 0 to 2. So clearly this negative value that I'm getting here, I am not interested in. So I'll just say not in interval. So I don't care about that value. This value, I guess I can clean this up a little bit. I can say we get 2 over radical 3 equaling x. And that is going to be my one critical point in this interval. Now 2 over radical 3, what does that mean to me? Maybe I should go ahead and figure out what that is. So I'll go ahead and just chuck this in a calculator. So 2 over radical 3 is going to be 1.154 dot dot dot. And that seems reasonable to me because that's somewhere between 0 and 2. It's not exactly halfway, but it's close to halfway. Halfway would be 1. So that seems like a reasonable point to me. Now, that's not to say that this is my maximum. I mean, obviously, I think we know it's going to be, but you really haven't justified or verified that yet, right? When you take a derivative and you set it equal to 0, the critical point that you get could yield a minimum, but it could also yield a maximum, and relative ones at that. So what we really need to do is verify or justify, I should say, that this thing represents where my absolute max is going to occur at. And to do that, that's when we bring in the concept of the extreme value theorem. So I like to write by the extreme value theorem, which again, the extreme value theorem, all it says is I'm guaranteed to have a max and a min of a continuous function on a closed interval. It's an existence theorem, but I like to write by the extreme value theorem. I'm going to go ahead now and I'm going to test my endpoints and I'm going to test my critical point to see what I got going on. So test it where? Well, you want to test it in the original function and compare those values that we talked about before, those y values. So I'm going to do a of 0, and I'm going to do a of 2. So a of 0, let me chuck 0 into my area function. Well, 2 times 0 is 0. Anything, 0 times anything is going to be 0. So I get 0 for that. All right. What does that correspond to in the picture that we talked about? Well, actually, I didn't talk about this one. If x was 0, then your vertex would be just that, right up top. There would kind of be a vertical line. So that would be a degenerate rectangle of area 0. If I do a of 2, and I chuck 2 in here, 2 squared is 4, 4 minus 4 is 0, I'd get 4 times 0, which of course is 0. And that was represented when x was 2 by this flat rectangle. All right? So somewhere in between must be that rectangle of most area, and turns out it's going to happen at this critical point. So if I did a of 2 over radical 3, that's going to give me the value that is the largest area. So I'm going to have to go ahead and figure that out right now because I have not done that. So what I can talk about what I'm doing right now is I actually did 2 over radical 3 in my calculator, and I stored that value as a. And now what I'm going to do, rather than typing in 2 over radical 3 all the time, I'm just going to type a in. So I'm going to go ahead and do 8a in my calculator minus 2a and then cubed. Maybe I should be writing this out for you, but I'm not going to. So I'm going to get 6.158 dot dot dot. So all I got to do now in my optimization problem, I tell everyone, you do the optimization problem, write what you did. What did you find here? What the heck's going on? Well, it turns out that if x was equal to 2 over radical 3, so in other words, 1.154, right? And that was the x value right here. When you get this vertex here, that's going to inscribe a rectangle that has the largest area, and that area is going to be 6.158 square units. Now, a lot of times they'll ask you for the optimal dimensions. Right, so the dimensions in this case I'd give us the largest area. Well, what are they going to be? Is that x? Is x one of those dimensions? And if you remember, it wasn't. 2x was one of those dimensions. So why don't I do this? Why don't I just say, hey, listen, let's let a equal 1.154. Remember, that was our critical value x. So then the optimal dimensions are going to be 2a, whatever that works out to be, by the y value, which how do you get the y value? Well, you have a formula for it here. So it would be by 4 minus a squared. And these would be your optimal dimensions. So you can go ahead and plug that in your calculator if you want. I'm going to choose not to. So there you go. So basically, we found the rectangle inscribed under this little parabola here that is going to produce the largest area possible.